Welcome to another GCBASIC tutorial for the PIC18FxQ35 chip family. Let's get straight into it. This is part 9, timers and timer interrupts. Exciting stuff. No, seriously, this is very interesting stuff. Please like this video and subscribe to the channel. It all helps in the metrics. Thank you. So we are going to be looking at a timer 0 overflow. It just represents any of the timers. How you can use an 8-bit timer and a 16-bit timer just to flash the LEDs. As an example, we will be building upon what we've done in the past. So straight in. I'm using a PIC-dem2 demonstration board. Why? Because it's on my desktop. And I'm using a whole series of capabilities, but today we'll be using the LCD and the serial just for outputs. Oh, and the LEDs, I would imagine. Okay. It looks like this. LCD where I left it yesterday, some LEDs here, and I've got a serial connection coming out of junction 18. Come back to that picture in a moment. Inside of the PIC-dem Plus demonstration board and in this tutorial there is a PDF which shows you reference architecture and schematics, so you don't have to struggle. Look, I want to recap this. VDDIO2 domain power. I have got VDDIO2 power because think of it like this: no power on that, no domain IO, and I am using the green domain, the secondary domain. So you must apply power. I'll bring the pen up. You must apply power to VDIO2 to get any of the green ports to work properly. Okay, and I'm using one of them. Okay, so actually I'm using more of them. I think I'm using all RD, the D, port RD. My brain's gone. A port D. So I have got that hooked up. Let's have a look at the big desk cam here. Look, I've got it hooked up here, this yellow cable, 5 volts into that particular port. Click cracking. Timer primer. Look, timers can generate very accurate delays. You can use the internal clock or external clock. The microcontroller can generate time by calculating it, which we've seen it through the weight control, but we can also relieve the CPU by using an internal timer. And we can change the pulse rate of that by using something called prescalers and postscalers. But a timer is very, very simple. It's just a binary counter that's counting away, and when it gets to the end of a cycle, it generates what's called an overflow. And it will set a flag. And if you've enabled the interrupt, it will get passed to the interrupt handler. So it's quite simple. This diagram I've got, we're going to peel back in a moment. So how does it all work? Well, there's only a couple of commands. There's init a timer. I'll just bring my pen up. Init, I'm going to init timer 0. I give it some parameters, start that timer, and set that timer. You can do it in the other order if you wish, just for perfection. Effectively, I've given there in the GCBASIC install there is a number of tools for the enhanced 8-bit timer, which we're going to be looking at as well. But just ask your AI now. It will generate GCBASIC code for those 3 commands. Just give it that, and it will help you. So let's have a look how it all works. This is the block diagram that's inside of the datasheet. It says we're going to use, in here it says, well, I'm going to use the main clock divided by 4. So I'm going to put a prescaler into this register. I'm going to put a postscaler into this register, and I'm going to check a flag here. It's not a great diagram. It's for a beginner, it's not a nice diagram. Think of it like this. Inside of one of those diagrams, in here, let me just bring my pen back up. Here, pen. It's not even clear what this does here. You've got an input and an output. What's the difference? Well, if you have got an 8-bit timer, it does it one way. And if you wanted a 16-bit timer, does it a different way. And what the difference is that in an 8-bit timer, you use a 1 register as a byte, the low part, and if you're using a 16-bit register, you use 2. Let me just bring my pointer back. 2 registers, like that. And they're added together into a word because the number's bigger. And it enables you to have much larger timers. So how does it work? As I said, they can generate accurate time delays. So let's walk through this diagram. The first thing you need to do is do a clock select. Are you going to use the internal oscillator or an external clock signal? And that needs to be set up. It generates a small signal, but it's quite a high frequency. Well, you can prescale that between a range between one number and another number, and that's pretty well known in the data sheet. So that's quite a large prescaler, and that slows the clock signal down, but not enough normally. You can post-scale it. So now you've done the prescaler, now you can post-scale it, and it gets that signal much, much longer. So you can actually take the internal clock at 60 megahertz and make it into a 10 millisecond signal. If you've got the timer enabled, it will then start to set the timer in a particular timer. And you've got many different timers. We're using timers 0, 1, 2, all the same. And as it changes the edge on the clock signal, it will increment in that number. I'm doing it in hexadecimal, just for effect, I guess. And it carries on incrementing until it gets to FE. And when it rolls over, FF, when it rolls over, it resets the counter back to 0 because it's a byte value. It sets an overflow flag, which we can go and test. And it does that regardless of whether the interrupts are running, it just does it. And so once that's set, we can test that and go, what's happened? And then use it. And then if you've got the interrupt enabled, it will then call the interrupt vectors and it will get passed to a handler that you've written. And we've got an interrupt. So there's 2 things in here. The timer overflow flag is set regardless. You don't need the interrupt or enabled. You can just test that. And we're going to show that, okay? We're going to do both methods. We're going to use the interrupt method and the overflow method just to see it all work. So we're going to look at some code, obviously. We're going to do a timer 0 overflow, 8-bit timer, and a 16-bit timer, and the advantages of both. Let's open up GC Studio. GC Studio, started it up. There we go. I'll just zoom in on that. I've done that lots of times, and I'm just going to open up the folder, which is the 18F recent folder. This is the code where I left it, I guess. Yeah, it is. Yeah. I have been doing other work, so I have to come back and reset to kid myself that I've not been here before. So where are we? On the desk cam, we've got the timers running. We've got this button, haven't we? Yeah, it does left and right, and it does stuff, okay? So back to where we are. Open up 110, rotate the LEDs using timer overflow event. Okay, let's just Control B, that left-hand window, Control J, the bottom window, and I don't have anything on the screen, so I did not select it. There we go. I've selected it now. Let's go to the top. Look, this is a big program because so much comments in there for you lot. VDIO2 is critical. I've got the chip. Oh, look, I have decided to lower the frequency on the chip. I'm saying 16 megahertz. There's a reason for that. You can figure that out later. All the hardware is the same. I'm going to leave the serial connection up because that's quite useful. So I'm going to be using the hardware serial connection that we have hooked up on RC6. All the LEDs are all the same. And there's the baud rate connection. Here's your setup for the LCD, see the previous videos, and the power for this particular ocular driver. So the first thing it's going to do is put started on our serial terminal. You could do the same on the, I guess you could do the same on the LCD. Why don't we do it now? Look. Print started. There we go. Not the best use of strings, but never mind, eh? Initialize the timer. So how are we going to initialize this timer? Well, for this particular calculations, we just need to set the oscillator divided by 4, which is called FOSC, or oscillator. We're going to set a prescaler to 256 and a postscaler of 1. And that will give us an interrupt of 10 milliseconds. It will. You can calculate that on your own. There's lots of calculators in the inside of GCBASIC installation. And this is the command. Init timer 0. I'm using the internal oscillator with a prescaler of 256. I want to use I'm going to be explicit and tell it I need timer 0 because you can actually change this frequency here, and a postscaler. And this is the command to get it to work. This is how you say prescaler and postscaler. Very simple. Start that timer. That bugged me when I saw that in the I'm going to change it in the PowerPoint. I think that's a better way of doing it. So for every 10 milliseconds, we're going to say put a little 8-bit number in there. Every 10 milliseconds, it will set a flag, and it will set the flag that we spoke about earlier on. And then I'm going to start that timer. Great. Look, so now we've got it running. The clock's running. It's incrementing it, and every 10 milliseconds, it's going to call an interrupt. Well, how does it do that? Forget the variables for the time being, because not important. On interrupt, timer overflow, timer 0 overflow, call the ISR. And this will set up the interrupt handler automatically. It will set the flags, it will set the interrupt itself. Where do I get that from if you don't remember? Function key F4, PIC-info. Or you can go to the data sheet, yeah. But I'd rather that you go in here because it's a lot easier. Let me just look in here. Interrupts. Have I got the right chip selected? I have. And these are all the interrupts that you can specify. And the one we're specifying is timer 0. Sorry about that. Timer 0 overflow. And it will automatically test. It will set the enable interrupt for you. And this is the flag interrupt. It will test on its own. But we're going to come back to that and test it. So on interrupt timer 0 overflow, call ISR. Have I got a routine called ISR? I have. Interrupt service routine. And it increments a variable that I have defined called timeout. And so it's going to have a timer. And that will just increment it. Every time it goes there, it's just going to increment it. So in my program, I'm just going to say, when the timeout is 100, put some stuff on the screen. It changes the LEDs and resets the timeout to 0. So every 100 times it will run the LEDs, and we know that the interrupt will run every 10 milliseconds. Therefore, we should see an interrupt, a set of events happen every second. Function key F5. Now I've got the terminal hooked up. Let me bring the terminal in. I've got this hooked up. It says started, exactly what we saw, and we've got some dots. You can wade in to see what this all does, but I'm going to turn the time on in here. The time. That is pretty good. That's an internal oscillator, uncalibrated, every second. Pretty easily done. So what do? We set the postscaler and the prescaler postscaler. We gave it a value, which is we set the timer, and then we call the interrupt to every 10 milliseconds, count 100 of those, and we put some stuff on the screen. Big desk cam. Oh, look at that. We should change that really. I'm going to make this code really nice for you. Yeah, I am going to just change the code. Wait 1 second. Wait 2 seconds. I am clear. I'm just changing the screen because I don't like that display on the LCD. The LCD here is quite interesting actually. I'll do it a different way. On the code here, it says get the character, whatever's at 0 on the screen, look. It replaces it with another character. You can, as I said, in here, you can figure out what it's doing on its own. I'm going to get rid of, so I'm going to locate. I don't know what to do. I'm struggling here. Okay. I'm going to leave it as it was. Okay. All right. Get rid of that. Get rid of that. That's a bit naughty. So function key F5 to reprogram it. We'll look at what's going on here. Here we go. Started. I'll bring the terminal in as well, just to further complicate things. Where's the terminal? There we go. So we've got everything on the screen. LED flashing. We've got LCD flashing, and the terminal incrementing every second. Look, not calibrated. It's not an external clock. It's good enough for military work. Okay. So that's quite a simple program. Let's look at a bit more, a bit better, a bit more interesting. So even in this, we've shown you how to do an interrupt service routine. Keep them short, and they're very, very useful. Let's look at an 8-bit timer. That was an 8-bit timer, but it was using an interrupt. So I want to recap an 8-bit timer. Same hardware, so I'm not going to go into the hardware here. Exactly the same hardware. But what we can do is I've set it up so that it's interrupting every 10 milliseconds. There's no interrupt. There is no interrupt routine in here. What we're doing, we're testing that flag TMR0IF, which means has the interrupt flag for that particular event, which is an event that was documented in PIC-info. Remember? If we zoom in, let's look at TMR. Oh, I put it on timer. Yeah, timer 0 overflow. That flag is still set, so I can test for that in my code look and just go wait here until whilst it's 0, because I clear at the moment it's not 0, and so I can just increment things very easily. Function key F5. Let's look what it does. So it's a flag. It's always set. So we can actually rotate things. We can use an interrupt or not an interrupt. Depends what you want to do. It's totally down to you. So what we're seeing here on big desk cam, LEDs are rotating. Have I got anything on the terminal for this one? Let's have a look at the code. I'm looking at the code now. We've got a serial output of a dot. Look, there we go. Let's have a look at the serial output. Every second. So I'm counting 100 of those. If the count is 100, then put the dot on the screen. But what we've done quite clearly before then, okay, is ensured that things are set up. So here we go, a do loop forever. It says here, wait for that event to happen, not the interrupt. It's the event in the register bit called TMR0IF equals 0. So you can talk direct in GCBASIC, you can talk direct to the register bits. Really simple, just talk to them like that. You can do whatever you want to do. And then I'm clearing it, and then I'm resetting the timer because I need to reset it. That's the process. And then I just increment my timer up. And then if it's 100 of those, it's done. But this is all complicated. Surely we can count a second. Well, of course you can. If you look at the next program, 130, rotate the LEDs using a 16-bit timer. We're going to put a 16-bit value in, which is what we saw earlier on, and we can extend the calculations within the microcontroller to cover a much larger number, and therefore we don't need to sub-count all these things in terms of 100 and that. So basically tell the compiler that you're going to use 16-bit timers for this program on timer 0, 16-bit. Pass it the init cycle, and I'm going to actually tell it to do this. Let's have a look at the calculations. I want it every 1 second. And so that 1 second, I've been able to calculate that by saying, right, I've got 16 megahertz instruction clock cycle, therefore I've got a timer of 250 nanoseconds, and through this calculation I can preload it with a 16-bit value of OBDC, which is equivalent to 3036. And if I set that timer to that, which is a large number, I don't need to count 100 of something. It's a much larger unit of calculation of scaling the initial timer. Same process. I'm going to wait until the timer is set to 0, and the moment that flag is set, I'm going to clear it and then reset it at the bottom. There you go. I just reset it at the bottom there. So this is a 16-bit timer because I've set this constant and I'm actually passing it a word value, function key F5. What's he going to do? He's going to put it on, it's going to flash the LEDs, I guess. Every second it will flash the LEDs. One on, next one on, next one on. Great, that's superb. Let's have a look at the desktop. In here, I'll bring in the terminal. Now it's using a different timer, and that is okay for military workload. Yeah, 26.5, 27, 20. Look, extremely simple. But in this case, we're not using the interrupt, we're using timer, the interrupt flag itself. And you can do that for all the timers. It's extremely simple. You can also use all the register codes. You can go to your favorite AI engine, not do any of this, and just set the interrupt. You can use the registers directly, but the easy way is just to do this. Init the timer, set the timer value, and start it. Really, really easy. So what we've just done, set the LEDs to rotate every second. The rotation code, not interested in that. We're focusing here on the timers. With that, back to PowerPoint. So, we have a quick look at timers and all the different types of timers. But next time we're going to look at EPROMs, which is a set of memory, and we're going to put that out in the serial terminal because it's quite interesting. Enjoy.